సార్
చెప్పు.
సార్ అదే మీరు చెప్పేటువంటి నోట్స్ కనుక మాకు ఏమన్నా గ్రూపులో ఏమైనా పెడతారా అనేసి అడిగారు.
ఏమంటారు?
ఇప్పుడు మీరు చెప్పే నోట్స్ ఉంది కదా సార్,
ఆ,
అదే ఏమన్నా గ్రూప్ లో అంటే ఒక మెటీ అంటే నోట్స్ లో అంటే ఏమన్నా గ్రూప్ లో ఏమైనా పెడతారా అనేసి అడిగారు సార్.
దీంట్లో యూట్యూబ్ లో మీరు డౌన్లోడ్ చేసుకుంటే వస్తుందని నాకు చెప్పారు, అడిగాను నేను.
సార్.
ఇది ఉన్నాయి కదా యూట్యూబ్ లో, వాళ్ళు అప్లోడ్ చేస్తారంట
ఆ,
మా యూనివర్సిటీ వాళ్ళు. మీరు మిమ్మల్ని డౌన్లోడ్ చేసుకోమని చెప్పారు, నేను అడిగాను.
ఓకే సార్.
ఓకే. టుడే we are discussing about, dear students, unit 14. Unit 14, connected topological spaces. Unit 14, connected topological spaces. Connected topological spaces. Topological. Connected topological spaces. Connected topological spaces. Concepts. Concepts. Definition. 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 The topological space X and tau. A TP means topological space. X comma tau is said to be connected. Is said to be connected is said to be connected is said to be connected if X cannot be expressed, if X cannot be expressed, X cannot be expressed as a disjoint union of, as a page number 118, as a disjoint union of two non-empty disjoint union of disjoint union of two non-empty open subsets, non-empty open subset, open subsets, open subsets, open subsets, open subset of X. G and H are two non-empty subsets of X. Let G and H are two non-empty, two non-empty, two non-empty subsets of X, subsets of X, two non-empty subset of X, and G intersection is null set, and because these two are disjoint sets, no? G intersection H equal to null set by generator. That equal to, that implies X is not equal to, X is not equal to X is not equal to G union H. G union H. G union H. A topological space X tau is said to be TP means topological space. SP means space. A topological space X comma tau. X comma tau. Tau is said to be disconnected. Is said to be is said to be said to be disconnected disconnected disconnected. If it is not connected, disconnect is not connected. Not connected is not connected. There exist two non-empty disjoint open sets. There exist two non-empty open non-empty non-empty disjoint open sets A and B. Disjoint open sets A and B. A and B. A and B. In X. In X. A and B. Such that X equal to A and B. Such that X equal to A union B. A union B. Such that X equal to A union B. In this case, the pair A comma B. In this case, the pair A comma B. Pair A comma B. A comma. Is called disconnection of X. Is called a disconnection of X. Is called a disconnection of X. Disconnection of X. Disconnection of X. Disconnection of X. is called a disconnection of X. It's called a disconnection of X. Example. Definition is the example. Let X comma tau be a trivial topological space. Let X comma tau be a trivial topology, trivial TP means topology, trivial topology. Trivial topology. Space or indiscrete topology space. SP means space. Or indiscrete, indiscrete, indiscrete topological space, topological space, topological space. Then X is a connected since then X is a connected space, connected connected since the only non-empty open subset of X since only non-empty 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 open subset of X non-empty open subset of X when subset of X then and hence X cannot be expressed as a union of two non-empty open subset of X. Of X is X. X is X. And hence X cannot be, and hence X cannot be X cannot be X cannot be expressed as a expressed as a expressed as a union of two non-empty open sets. Union of two non-empty two non-empty two non-empty two non-empty open subsets of X. Open subsets of X. Non-empty open subsets of X. Open set. So using this one important theorem, page number 119. Page number 119. Page number 119. Theorem. 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 Formation is let through that or through that, through that or through. Question formation is like that. Through that. X be a topological space. X be a PP means topological. SP means topological space. Topological space consisting of two or more elements. Consisting of two or more elements. Two or more elements. Two or more elements. Then the following statements are equivalent to each other. Then the following statements are statements are statements are equivalent to each other. 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 First statement. Equivalent to each other. X is disconnected. X is disconnected. X is disconnected. Second, X can be expressed. X can be expressed. X can be expressed as disjoint union of as disjoint union of as disjoint union of two non-empty proper closed two non-empty proper closed subset closed subset proper closed subset of X. Third one. There exists a proper subset of X. There exists a proper subset of X proper subset of it, which is both open and closed, which is both open and closed, which is both open and closed. Proof. One implies two. One implies two. One implies. Let X be a disconnected space. Disconnected space. Let X be a disconnected space. SP means space. X is disconnected, that implies X is disconnected. Disconnected. That implies there exist two non-empty open sets. That implies there exists two non-empty open subsets. Two non-empty. Two non-empty open subsets. Open subsets. Open subsets. G and H of X. G and H of X. H of X. With X equal to G union H. With capital X equal to G union H. G union H. And G intersection H equal to null set. G intersection H equal to null set. Null set. G equal to X minus H. That implies G equal to X minus H. G equal to X minus H. That equal to H dash. To H dash. H dash. And X minus G equal to G dash. And X minus G equal to G dash. That equal to H. That equal to H. Also, G and H are proper non-empty open subset of X. Also, G and H are proper G and H. G and H are proper non-empty open subsets of X. Proper non-empty open subset of X. Open subset of X. That implies G dash. That implies dash. That equal to H. And H dash equal to G. H dash equal to H dash equal to G. C dash equal to G. Are two non-empty proper closed subset of X. Are two non-empty two non-empty two non-empty proper closed subset of X. Proper closed subset of X. Subset of X. Subset of X. Hence X equal to G union H. Hence X equal to G union H. Union H. Where H, G and H are two disjoint, where G and H are two disjoint disjoint two disjoint non-empty proper closed non-empty non-empty closed proper closed subset of X. Subset of X. Subset of X. Hence 1 implies 2. Hence 1 implies 2. So now we need to prove that 2 implies 3. 2 implies 3. Assume 2 is left 2. That is X equal to A union B. X equal to A union B. X equal to A union B. Where A and B are two non-empty open, where A and B, where A and B, A and B are A and B are two non-empty open, two non-empty two non-empty open proper closed sets. Open for closed subset. Proper closed subset. Open proper closed subset of X with A intersection B is null set, with A intersection B null set, section B is null set. A is proper non-empty closed set. Now A is proper non-empty proper non-empty proper non-empty open subset of X. Non-empty closed proper non-empty closed subset of X. Closed subset of X. Subset of X. equal x equal to A union B equal to A union B. X equal to A union B. X equal to A union B. A intersection B is null set. A intersection B. A intersection B is null set equal to null set. That equal to A dash. So A dash. A dash is nothing but complement. A dash is x minus A. X minus A. That equal to B. X minus is a proper non-empty open subset of X. And is proper non-empty proper non-empty is proper non-empty open subset of X. Set of subset of X. Proper subset of. Hence B is a proper non-empty subset. Hence B is the hence B is the proper non-empty subset of X. Proper non-empty non-empty proper non-empty subset of X. Subset of X. Subset of X. Which is both open and closed in X. Which is both open and closed in X. Closed in X. Open and closed in X. Observe that A is also both open and closed proper set of X. That implies 2 implies 3. Next, third one. Third implies 1. Third implies 1. Like a cyclic order. Third implies 1. Let or assume third and let A be non-empty subset of X. And let let A be non-empty subset of X. Non-empty subset of X. Non-empty subset of X. Non-empty subset of X. Which is both open and closed. Which is both open and closed. Open and closed. Both open and closed. Both open and closed. A is not equal to null set. Not equal to null set. A is not equal to null set. not equal to null set is a non-empty proper subset of is a non-empty is a non-empty is a non-empty proper subset of which is both closed, which is both unclosed, is both closed. That implies A dash or A complement again, is non-empty proper subset of X. Is non-empty proper subset of X. Non-empty proper subset of X, which is both open and closed, which is both open and closed. And closed. Both open and closed. Hence, X equal to A union A dash. Capital X equal to A union A dash. And A intersection A dash. And A intersection A dash. Intersection A dash equal to pi. That equal to X is discontinued. That implies X is discontinued. X is discontinued. Hence, proof. This completes the proof of theorem. Then, one more important theorem. Page number 121. Page number 121. Page number 121. Page number 121. Prove that or show that question formation is like that. For 10 marks important. Or show that y, X and Y be two topological spaces. Let X and Y be two topological spaces. TP means topological. SP means space. SPS means spaces. F X to Y be a continuous function. F X to Y be a continuous function. Continuous function. If X is connected, the X is connected. X is connected then f of x is connected in y. Then x is connected. F of x is connected in y. Connected in y. Connected. That is, any continuous image of connected space is connected. So sometimes they will ask this question. So prove that any continuous image of connected spaces is connected. Or this question one, prove that, or show that, show that any continuous image of any continuous image of any continuous image of connected spaces is connected. Connected space is connected. Connected. Connected space is connected. Proof. Proof of the theorem. Let X be a connected topological space. X be a connected topological space. Connected topological spaces. Topological space. And Y be another topological space. Y be another but Y be another topological space. Another topological space. Let F x to y be continuous function. Continuous function. Fn means function. Function from x to y. From x to y. X to y. From x to y. Now show that f of x is discontinued. Now show that f to y is disconnected. 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 That implies there exists. That implies there exists That implies there exists two non-empty open subset, two non-empty open subset, two non-empty open subset G and H, G and H in Y such that Y such that f of x intersection G, f of x intersection G equal to null set, equal to null set. That means f of x intersection H is also null set, also null set, is also not equal to null set. This is also f of x intersection G is not equal to null set. F of x intersection H is also not equal to null set. And f of x subset, f of x subset of x G union H. Now f of x is subset f of x subset union subset G union H. That implies x equal to x equal to f inverse G, f inverse G union f inverse H, union f inverse H, f inverse H. Subset are equal to x. Subset are equal to x. That equal to subset are equal to x. That implies x equal to f inverse G, f inverse G, f inverse G, union f inverse H, union f inverse H, inverse H, f inverse H, f inverse H, f inverse H. F inverse H. Also f of x intersection G. So f of x intersection G is not equal to null set. F of x intersection H is not equal to f of x. Already we wrote this. F of x intersection H is not equal to null set. 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 Both F inverse G and F inverse H are non-empty sets. Both with F inverse G, F inverse G, and F inverse H, F inverse H are non-empty, or non-empty, or non-empty, or non-empty. F inverse G, F inverse H are open subsets of X. Here, F inverse G and F inverse H, F inverse H are open subsets, or open subsets of X. Open subset of X. Open subset of X. And X equal to, and X equal to F inverse G, F inverse G, F inverse G, union F inverse H, F inverse H. Finally, we have that. Finally, we have that implies F inverse G intersection F inverse H, F inverse H, F inverse H equal to is non-empty, means null set equal to null set. So X equal to F inverse G, F inverse G equal to F inverse G. Belongs to F inverse G. X belongs to F inverse G intersection F inverse H, F inverse H, F inverse H, that equal to F of X equal to X belongs to H, that equal to F of X, F of X belongs to H. Belongs to H. Which is contradiction to the fact, which is contradiction to the fact contradiction to the fact F inverse G intersection Y, F inverse G intersection Y, intersection Y, intersection F inverse H, intersection F inverse H, intersection Y, intersection Y, that equal to Y. Hence X is disconnected. Hence X is disconnected. X is distinct. This is contradiction. This is a contradiction. This is a contradiction. Which is a contradiction. Is a contradiction. Hence, f of x must be connected. Hence, f of x must be connected. Must be connected. Must be connected. Hence, proved. Hence, proved. This completes the theorem. Okay. One more theorem is there, 10 marks. We have to do this homework. Page number 122. Page number 122. 122. Theorem number 14.4.5. Theorem for 10 marks. 10 marks. Next. Unit 15 components. Unit 15. Unit 15. Components. Unit 15 components. Concepts. Definition. 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 Let x comma tau be let x comma tau be topological space. TP means topological. SP means topological space. A connected subspace C of X. A connected subspace. Subspace. A connected subspace C of X. C of X is said to be a component. Is said to be a component is said to be a component said to be a component is said to be a component of X. Component of X is said to be a component of X. If it is not properly contained, if it is not properly contained, yeah, properly contained, and any subset of matter contained in any other connected subspace of X. In any other connected subspace of X. In any other connected subspace of X. Other connected subspace of X. Subspace of X. That is C. Is C. Is a maximal connected subspace of X. Is a maximal. Is a maximal. Maximal. Is a maximal. Connected subspace of X. Connected. Connected subspace of X. Subspace of X. Maximal subspace of X. Subspace of X. Example. Example. Let X comma tau be a discrete topological space, comma tau be a discrete topological space, discrete topological space containing more than one element, containing more than one element, containing more than one element, then there is a singleton sets are connected, then they have that, then they have that then they have that they have that then they have that singleton sets are connected, singleton sets are connected. Single cell sets are connected. Sets are connected. Any subset of X containing more than one element, any subset of X any subset of X containing more than one element, more than one element, one element, more than one element, disconnected, disconnected, disconnected. And singleton sets are the hence singleton sets are the singleton sets are the singleton sets are the only components of X. Only components of X. Components of X. So using this, we'll prove one theorem that is for 10 marks. Page number 125. Page number 125. Theorem. Prove that or show that. Question formation is like that. Or show that. Do that or show that. X be a topological space. X be a topological space. X be a topological space. And A be a connected surface of X. And A be connected A be a connected subspace of X. Subspace of X. Connected subspace of X. Then any subspace of V of X. Then any subspace of V of X. 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 With A subset. With A subset. B subset of complement of A bar. Complement of A bar is also connected. Is also connected. Also connected. Question formation is like that. Proof. Proof of this theorem. Simple and easy also. Let A be a connected subspace of X. Let A be a connected subspace of X. Sub Connected subspace of X. Connected subspace of X. And B be the subspace of X. And B be the subspace of X. Subspace of X. Subspace of X. With A subset, B subset, A bar. With A subset, B subset, A bar. B subset, B subset, A bar. If possible, B is not connected. If possible, B is not connected. B is not connected. B is not connected. B is not connected. Therefore, there exist two open sets. Therefore, there exist two open sets. Two open sets. Open sets. G and H of X. 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 With G intersection B is not equal to not set. With G intersection B is not equal to null set. B intersection H. B intersection H is not equal to null set. Not equal to B subset B union H. B subset G union H. G union H. G union H. Now A subset B. A subset B. Now A subset. A subset. A is connected. A is connected. A is connected. That implies A subset are equal to A subset G. That implies A subset G. A subset G. A subset G. Or A subset H. A subset H. A subset H. Since A union A subset, since A subset G union H. A subset G union H. Let A intersection H is not set. A intersection H is null set. A intersection H is null set. Now H is open. H is open. H is open. H is open. A intersection H is null set. A intersection H is null set. Phi means null set. So closure of A intersection H is null set. Closure of A intersection H equal to null set. Null set. B intersection H equal to null set. That implies B intersection H equal to null set. Null set. Null set. So a contradiction, similarly, a contradiction contradiction, contradiction. Similarly, similarly, contradiction, similarly. A intersection G is A intersection A intersection G is null set. A intersection G is null set. That is what it. B intersection G is null set. B intersection G equal to null set. B intersection G is null set. Yes. A contradiction. A contradiction. A contradiction is contradiction. Is contradiction. Hence, B must be connected. Hence, B must be. B must be connected. B must be connected. B must be connected. Subspace of X. Subspace of X must be connected. Subspace. This completes the theme. Hence, proof. Important for 10 marks. Hence, proof. So this in this chapter, one definition and one theorem we discussed. That is 10 marks. This is for 10 marks. Okay. Okay, these two chapters. Next, then we'll meet on Saturday. Thank you very much, all of you.